Good morning. So the stream should be live and you should be able to hear me, and the sound should work. Thank you for confirming that. I see one thumbs up already. Excellent. Um, after the entire semester, everyone knows that the first thing I'm going to ask is to give me a thumbs up when you can hear me. So what we're going to do today is talk about relativity. And so this is, of course, technically it's in University Physics 3. It's in volume 3 of the textbook, and it uses a little bit of the justification in electricity and magnetism, but we are going to not use that justification. Oops, those were my notes. So we're not going to use the... Come on, move over. Thank you. So we're not going to use the details of the justification that's in electricity and magnetism, because that's something you're only going to see in the next level of the course. But I hope the concepts of relativity and special relativity in particular will be useful regardless. So what we're going to do first is we're going to talk about physical laws. In particular, we're going to talk about where physical laws should apply. If we have, in physics, if we come up with physical laws, we want them to be valid not just in whatever reference frame we are working in. We want them to be valid beyond that single reference frame, right? So if we look at, for example, Newton's law, so F is, and I'm just going to use Newton's second law here. So Newton's second law, F equals ma, is valid. Are you still seeing the stream, or is there a problem with the stream? Anyone who can confirm that the stream is still working? Okay, I see thumbs up. Okay, so maybe Julian, you have just a individual problem in your end. So Newton's law, F equals ma, that is valid in some reference frame, right? Reference frame 1, in some condition, some set of coordinates, a coordinate system. What if we now go to a different coordinate system? So if we go to reference frame 2, and we have the velocity of reference frame 2 in reference frame 1 is equal to u. So reference 2 with a velocity u as measured in reference frame 1. Reference frame 1. So that means that if I have my coordinates in reference frame 2, any coordinates in reference frame 2 will be the coordinates in reference frame 1, sorry, without a prime, plus u times t. So when there is some acceleration, so this is going to be, importantly, a constant velocity, so that if this is an inertial reference frame, then this remains an inertial reference frame because I'm not accelerating to go from one reference frame to another. So if there's this conversion, if there's this way of going from reference frame 1 to reference frame 2, then I can also calculate, of course, from that the velocity in reference frame 2 will be the velocity in reference frame 1 plus u. So the first one here is a v, and that's a u. And then, of course, the acceleration in reference frame 2 will be the acceleration in reference frame 1. And now we can go back and actually write that F is equal to m a prime as well. So our Newton's second law is valid in our first inertial reference frame, and it's also valid in another inertial reference frame that is moving with a constant velocity with respect to the first inertial reference frame. And of course, we could also add, a shift in the origin, which really is also something like a time coordinate shift. But anyway, so Newton's second law is valid in all inertial reference frames, which of course makes it a useful physical law. It's not something that only works as we happen to be here on the surface of the Earth. It works in any inertial reference frame, which is of course why it is a useful physical law. We want this to be true for all physical laws, though, and in particular, want it to be true also for electricity and magnetism. And this is the only thing about electricity and magnetism I'm going to say. And one of the outcomes, one of the observations of electricity and magnetism is that light has a velocity, has a speed c equals 3 times 10 to the 8 meters per second in vacuum. There's no dot there. In vacuum, and that is in any reference frame. So one of the outcomes of electricity and magnetism is that the speed of light in vacuum is 3 times 10 to the 8 meters per second. You know, it's a little bit more precise, this number, than that, but it is a fixed quantity. The speed of light is constant, it's unchanging. In vacuum, light will always have that speed. Now, how do we reconcile that with going to with the change in coordinate systems in Newton's law, while still maintaining that this statement has to be true in all reference frames? And we want the physical laws of both Newton's laws and the statement in electricity and magnetism that the speed of light in vacuum is a constant. We want both of those to be true. So when this was first encountered in the beginning of the 20th century, there were of course some questions about how these two things could be simultaneously true. How can the velocity be both transformed like this expression here, and how can the speed of light be constant in all reference frames? Now, the way around this is to essentially throw one of these things out, and that the insight of Einstein was to figure out which of those things to throw out. So instead of, in the case of Newton's law, instead of saying this is how I transform from one coordinate system to another, so that gives me that the velocity has to change like this, and therefore the physical laws are applicable in all inertial reference frames, Einstein turned this around, and Einstein introduced postulates, two postulates. The first one being that, as we said, all laws of physics must be the same in all reference frames. So instead of an outcome of the specific conversion to go from one reference frame to another, he made it the requirement. So the laws of physics must be valid in any inertial reference frame. And so that's the first postulate. So that says that the laws of electricity and magnetism have to be valid in any inertial reference frame. The laws that describe force and acceleration, Newton's law, has to be valid in any reference frame. Everything has to be valid. All of physical laws must be valid in any inertial reference frame. And we must now make sure that our laws of physics satisfy this requirement. And so sometimes this will mean that we have to change some of our laws around to be valid in any inertial reference frame. The second postulate was essentially the one that I've written there for electricity and magnetism. That's that the speed of light in vacuum has to be constant, is the same in any inertial reference frame and in any direction. No matter how you measure it, the speed of light in vacuum has to be the same. So instead of the speed of light being an outcome of electricity and magnetism, and instead of the unchanging nature of Newton's laws to be an outcome of how we transform our coordinates when we transition from one reference frame to another, Einstein made those a requirement. Is the stream again struggling? Okay, I think there might have been something with Gathertown. I just had a notice pop up on Gathertown that said there was a glitch. So okay, so yeah, you should be able to just go back to the YouTube stream. Thanks, Patrick, for posting it. So so what happens now with Einstein's postulates is that this is really just a transition. In particular, the first postulate is a transition in a long tradition in physics, where we started out with, as I said in one of the previous lectures, we started out with a heliocentric view of the universe. Sorry, we started off not with a heliocentric. We started off with a geocentric view of the universe, where the Earth is in the center of the universe and everything spins around the Earth. Then we went to a heliocentric viewpoint, where the sun is in the center of the universe and the Earth is moving around the sun. So we've kind of lost a little bit of our tendency of putting ourselves at the center of the universe. So we're now spinning around the center of the universe with the sun at the center. And now with Einstein's postulates, we're essentially saying that not even the sun is special. The sun is just one reference frame out of many, infinitely many, and it's not preferred over any of the other reference frames. Any reference frame, any inertial reference frame, should be able to describe all of our physics. So there's nothing special about the sun. There's nothing special about the Earth. Any reference frame should be able to describe the same physical laws. So I've used the word inertial reference frame here. So let me remind you of the definition there. So an inertial reference frame is the reference frame where essentially Newton's second law is satisfied if there's no forces that apply. So these are reference frames that are not moving with any acceleration. So no rotating reference frames like being on the surface of the Earth, but a reference frame that is moving with a constant velocity with respect to some other reference frame. It's a little bit of a circular definition in that sense. So then Einstein's postulates, again, laws of physics are the same in all reference frames, and light travels in vacuum with the same speed in all directions in all reference frames. Now there's some conclusions, some consequences of this of these postulates, and the first one, and usually these consequences, at least in the time when Einstein came up with these examples, they were thought experiments. They were not actual experiments that Einstein did. But they were thought experiments. The reason why these were not actual experiments is because typically the effects that we're going to be looking at now show up only when you have very high velocities. And at that time, those high velocities were not possible, or the precision needed to measure these effects at smaller velocities was not there yet. By now, we can actually do these measurements, and so they've gone from being thought experiments to being actual experiments. So one experiment is this, one thought experiment is this. We have a train that's moving with observer A sitting in the train. The train is moving to the right here. there's at the observer A is sitting right in the middle of the car, and there's two lights that are at the end of the car that the observer is sitting in. At the same time, on the platform, observer B is standing there. At exactly the time when observer A passes by observer B, those lights flash. So what happens now? As seen by observer B, what happens is that the light that was emitted at these times, at equal distances from observer B, is moving towards observer B and arrives at observer B at exactly the same time, right? So observer B sees both of those flashes at the same time and concludes that they were emitted at exactly the same time, because at the time when they were emitted, the observer B was just at the same distance from both of the sources of the light. So observer B thinks that the light was emitted at the same time. Observer A, however, has moved forward after the light was emitted. We'll see, therefore, the light from the light pulse that was emitted by the light at the front of the train. We'll see that light before the light that was emitted from the back of the train. Now, observer A in the train knows that there's the second postulate of special relativity by Einstein here. So observer A says, well, the speed of light in vacuum is independent, or the speed of light, let's assume that this person is in vacuum, which is of course not realistic, but so observer A knows that the speed of light doesn't depend on the direction, or doesn't depend on the inertial reference frame. So the speed of light must be the same for the light that is emitted from the back, from the light that's emitted from the front. And so observer A must conclude that because she's in the middle of the train, that the light was not emitted at the same time. So one of the conclusions that you cannot get around in special relativity is that there is no such thing as simultaneous events. If something happens at different points in space, in this case at the front of the train and the back of the train, then you cannot say that things happen at the same time at those points. Whether something happens at the same time, or in other words, the time difference between those two events will depend on the observer. So in this case, for observer B, it appears that the event of emitting light at the back of the train and the event of emitting light at the front of the train are simultaneous. Delta t is equal to 0 between those two events. For observer A, it doesn't appear that those are simultaneous events. For observer A, there will be a time difference between when the lights were flashing. And so that's one of the first conclusions from those postulates from Einstein, is that there is no such thing as simultaneity. There's no single statement that you can say that events are simultaneous if those events happen at different places, because depending on the motion of the observers, you can actually have a different outcome. So the events that happen at different places can be simultaneous, can be one before the other, or the other before the first, depending on the motion of the observer. So that might seem strange, but that is something that is an outcome from the postulates of special relativity. Now, this is only the start of the weird effects. Another weird effect is that times do not go at the same rate. So this is another thought experiment. And certainly in the beginning of the 20th century, when space travel wasn't anywhere near what it is now, this was definitely a thought experiment. So let's imagine that we have an astronaut in some spaceship who is bouncing light between two mirrors. So we have a light source here. The light bounces against this mirror, bounces back to a photodetector, and so we can measure the time it takes for the light to make that round trip time. So if we call this delta tau, tau was the Greek letter to distinguish it from delta t, which we're going to introduce in a second here. If this is delta tau, then with the speed of light in vacuum being constant, this will give us a time delta tau that must be 2 times that distance divided by the speed of light. So we're gonna derive how time changes this time dilation. So in the spaceship we have our mirror here, we have the light that goes there, bounces back. We have our source of light and our photo detector. This distance is d, so then delta tau is 2 times the distance over the speed of light, which we give the letter c. Now this is for the observer in the spaceship. This is for the astronaut who's traveling along with the setup. So for the astronaut who's moving along with the setup, the emission of the light and the detection of the light happen at the same place, essentially. Now there's an observer here on Earth who's watching all of this happen when the spaceship is moving at a velocity v. So what happens now is the light is emitted here. It bounces off the mirror when the mirror is here, and then it bounces back and goes to the detector when the detector is here. So the light, which is still traveling at the speed of light in vacuum, per our postulate, per Einstein's second postulate, the speed of light is the same. So that light travels now at distance s, and another times the distance s, which is going to be greater than d. And the time difference that the observer measures is delta t. So now we have our light that's emitted here, bounces off the mirror, and is detected by the photosensor here. And our delta t is, if this is now s, this is d, let's call this distance L, and this is distance L, then S will be the square root of d squared plus L squared, and delta t will be 2 times S over C, or 2 times, well, I'm not going to write any more details there. So the one other thing we know is what is L. So L is the distance that the spaceship travels when it's going at a velocity v. That's the distance the spaceship travels in delta t over 2. So that's going to be v times delta t over 2. So both of these things are true. Or delta tau is going to be this, or delta t is going to be that, and L is going to be that, and S is d squared plus L squared with the square root, or S squared is d squared plus L squared. So the only thing we've used here is Einstein's postulates of special relativity. So let's now look at S squared is d squared plus L squared. So if S squared is d squared plus L squared, we can actually relate some of these things with each other. So S squared, we're going to use S here and write this in terms of delta t. So S squared is C delta, or S is C delta t over 2. So that's C delta t over 2 squared. That's equal to d squared. So d is C delta tau over 2. That's C delta tau over 2 squared. And L is V delta t over 2 plus V delta t over 2 squared. So that's the expression we have that, again, must be true and is only following from or postulates of special relativity. Now we can, of course, divide out the c squared, multiply by 2 squared. So then we get delta t squared is delta tau squared plus, so we're multiplying here with 2 squared and dividing by c squared. So we get v over c squared delta t squared. And I can rewrite that now as delta t squared 1 minus v over c squared is equal to delta tau squared, or delta t is delta tau divided by the square root of 1 minus v over c squared. So the time that the observer on Earth measures between those two pulses, between the pulse being emitted and the pulse being received by the photodetector, is different from the time that the observer in the space station and in the spaceship measures. So the astronaut here measures delta tau. The observer on Earth, for the same event or for the same situation, is measuring this delta tau over square root of 1 minus v over c squared. And we're going to introduce a few variables here. So we're going to introduce beta is v over c. So that means that the velocity is beta times c. So this is the beta is the fraction of the speed of light. So that's the, remember, v is the speed of the spaceship. So that's the fraction of the speed of light with which the spaceship is traveling. So that's beta. So that means that we really have a 1 minus beta squared here. And we're going to introduce gamma as 1 over 1 minus beta squared as this factor. So then we end up with delta t is gamma times delta tau. So beta is going to be less than 1. Beta is less than 1 for speeds below the speed of light. And that means that gamma will be greater than 1. So that also means that delta t is going to be greater than delta tau. In fact, delta tau, which is the time that the observer in the space station measures, the astronaut measures, that is going to be a special time, which is partly why we write it with delta tau. Delta tau is, and it will be traditional to write this as tau instead of t. That is the so-called proper time. That is the time as measured. That's the time, I guess, interval in this case, but in general, time as measured by clocks at the same position, or clocks that don't move in that reference frame. So if we look at that in the drawing of on the slide here, the clock here between when the light is emitted and when the light is received, that's at the same position in the reference frame of the astronaut. So that time that is measured by the astronaut is called the proper time. Any time where the time is measured between points that are at different positions will not be the proper time. And in fact, any time that is measured by clocks that are at different positions will be larger than the proper time. The proper time is the smallest time that you can measure. The proper time is essentially what you measure if you are moving with the system that you're measuring the time of. So in this case, it's the time you measure if you are moving with that mirror system. Now, is this all relevant? I mean, obviously, I wouldn't be talking about it if it wasn't relevant. But one example where we can apply that is let's look at GPS satellites. if we look at a GPS satellite, we can actually tie this back to last week's material. So V orbit for a GPS satellite is square root of g times the mass of the Earth over the radius of the orbit. And if we think of a GPS satellite at 400 kilometers height, so we're going to do 6 times 6, 7, 10 to the minus 11 newtons meter squared per kilogram squared times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by 6,370, and I'm going to add 400 kilometers for the height of the orbit. So if I calculate this orbit, this velocity, that's 7,688 meters per second. And I can calculate my beta from that. The speed of light in vacuum, I don't think I've written down, well, I've written down the speed of light in vacuum. It's 3 times 10 to the 8, right? So it's V orbit over c, so 7,688 meters per second divided by 3 times 10 to the 8 meters per second. So beta is about, if you do the math, you'll find 2.6 10 to the minus 5. So a GPS satellite is going at a very small fraction of the speed of light, but it is a non-negligible fraction. It's of course it's non-zero, right? We can calculate from that what gamma is, or a relativistic gamma factor, and because of the fact that we have a square of beta here and we do 1 minus that, it actually becomes 1 minus a very small number. But ultimately gamma is going to be close to 1, but plus a small deviation from 1, which is given by this beta. You're going to need to use all of the digits on your calculator to be able to calculate this. But you'll find it's 1 plus 3 times 10 to the minus 10. So that's the factor with which we have to multiply the time as measured on a GPS satellite to get the time as measured on Earth. So on a GPS satellite, the time intervals delta t will appear longer than the same time interval measured on Earth. And now, of course, if you look at a time interval delta t of 1 day, that will result in a change. Delta t will be equal to delta tau plus about 26 microseconds. If you look at how much larger the day is as measured on Earth compared to the day measured by a GPS satellite, it's about this number of microseconds, 26 microseconds. And now, why does that measure? If we don't take into account the effect that this has, then if we're on Earth, let's say you're standing here with your phone in your hand and you're getting a signal from a GPS satellite over here, then the distance that corresponds with the light traveling for this additional extra time, if we don't take it into account, that c times 26 microseconds is about 8 kilometers. So after 1 day, if you don't take into account special relativity and time dilation, the fact that the time as measured on Earth is greater than the time as measured on the satellite, you would be wrong in the position determination from a GPS satellite by about 8 kilometers. So clearly this is a relevant effect if we are looking at things that move fast, even though this is still a lot smaller than the speed of light, and if we look at things that need to be very precise, for example, GPS position determination. So without special relativity, your GPS after 1 day would be wrong by 8 kilometers. This is kind of the summary of this. Now, there's other examples where the impact is even stronger, in particular when we get closer to the speed of light. And if we want to get closer to the speed of light, we have to typically look at particles in accelerated conditions. So if we have muons, particles that are created at high up in the atmosphere, if a muon is created with a high energy, and it takes on a speed that is close to the speed of light, then beta will be close to 1, and then gamma will be much greater than 1, and those muons will be able to travel very long. And this actually explains something that was observed when these muons were discovered first. Oops, there's an additional blank page. If we have the Earth here, and we have a muon that is created here. Muons have a half-life that is about 1.52 seconds. So if a muon is created, it will decay on average after 1.52 seconds. Now, if this muon is created here in the upper layers of the atmosphere with a low velocity, that would mean it will decay fairly high up in the atmosphere, and it will never be reaching the observers at the surface of the Earth here. Now, if a muon is created, so this is a beta that's close to 0. If a muon is created with a beta much greater than 0, okay, let's say beta about equal to 1. So what that will mean is gamma will now be much greater than 1, and delta t will be much greater than delta tau. And now the muon will actually, in its own reference frame, it still is moving at less than 1.52 seconds, less than its half-life, or it's on the order of magnitude of its half-life. But to the observer on the Earth, it will actually be moving at a different time, and that time will cause that muon to actually be able to reach the surface of the Earth. So we actually can see high energy, high velocity muons reaching the surface of the Earth, where low velocity muons don't reach the surface of the Earth, and that's caused again by the fact that our times, as we observe them, are actually longer without changing the time in the frame of reference of the muon, which is the time that determines when the muon will decay, or that sets the time scale for the muon to decay. So there's other examples here. The textbook introduces this twin paradox, where you could have two twins that start traveling, and one travels far away at high velocity and then travels back at high velocity. So the time of the observer on Earth supposedly has gone much, more time has passed between the event of leaving and the event of returning, so that the two twins are now at different ages. Now the paradox is that, well, you could think of this as the Earth actually moving in the opposite direction and coming back. But that's of course not a symmetric situation, because it's actually the ship that is accelerating, so we're not in an inertial reference frame anymore. So we've covered one of the big effects of special relativity, and that's that times are longer in the case of observers that are moving with respect to the system that you're measuring the time in. So the proper time is the shortest possible time that you can measure, and any observer that is moving with a velocity with respect to that time frame, that inertial reference frame, will measure a longer time. The other aspect is length contraction. So this is a very closely related effect, where if we have again a muon that is moving with a velocity, it will actually appear also to have an impact on the lengths that that you measure in that reference frame. And that is something we'll come back to on Wednesday. And then the one last thing we'll do on Wednesday is introduce the coordinate transformations to get from one coordinate system to another coordinate system that is moving with a high velocity. And we'll contrast that then with the Newtonian or Galilean coordinate transformations that we started off our class with today, which is this coordinate transformation. So we'll be able to look at a coordinate transformation in relativistic terms. And of course, in the limit of low velocities, we'll find back the original coordinate transformation. So that will be for Wednesday. And we'll talk to you then.